Okay, in this lecture, we're going to talk about inflationary cosmology. First, talk about how it solves so-called the initial condition problems. In chapter 10, we will be two major applications of cosmological constants: the cosmic inflation and the accelerating universe. Inflation in cosmology is the theory of the Big Bang itself. Besides solving the two serious issues regarding the initial conditions for the standard FLRW cosmology, more impressively, it provides the mechanism for particle production as well as for seeding the inhomogeneity required for the subsequent formation of cosmic structure. So this really, some sense, answered Fred Hoyle's original Big Bang objections. So let's first talk about initial condition problems. Uh, the FLRW cosmology describes very well the aftermath of the Big Bang. However, the model says very little about the nature of the Big Bang itself. Its success depends on initial value conditions that are so fine-tuned that just clamor out for explanation, especially so-called the flatness and horizon problems. So what is the flatness problem? We expect the expansion universe to slow down because gravitational attraction among matter and energy. Such deceleration, which means the second derivative of the scale factor is negative, means the time derivative of scale factor a dot must be ever decreasing function of cosmic time. As time increases, a dot must decrease. Now, Freeman equation can be written in terms of the mass density parameter omega, so like 1 minus omega equal to minus kc squared over a dot squared r. Shows a connection between the geometry k, the curvature, and the matter energy omega. Now, if k equal to 0, so 0 on the right hand side for flat geometry, we must have exactly omega equal to 1 all the time. Now, if k is not equal to 0, then the left hand side 1 minus omega must be ever increasing because the a dot square in the right hand side is ever decreasing because remember a dot is ever decreasing. So therefore the ratio must be ever increasing, which means omega equal to 1 is an unstable equilibrium point, meaning if omega ever deviates from 1, this deviation will increase with time because so in the curved space, which means k not equal to 0, expanding universe, the Freeman equation in this form shows that a omega equal to 1 is unstable equilibrium point. If ever deviates from 1, it will increase time. Or we say gravitational attraction always enhances any initial curvature. If you have some curvature, it can worse and worse. In light, this property is puzzling. The present time, the mass density is not too far from the critical density. It was right now 1 minus omega is order 1 or 0, but anyway, it's very close. It's not something a big number. This means omega must have been extreme close to 1, extreme flat in the cosmic past. Such a fine-tuned initial condition requires an explanation. Why is that universe in the past is so flat? So maybe we'll make it a little more quantitative. We'll calculate the deviation of density parameter from its flat universe value 1. Okay. Now, ever since the radiation matter equality time, which is at 73,000 years after the Big Bang, was a scale factor. That time, the equality time, scale factor about 1 over 10,000. the evolution of the universe has been dominated by non-relative matter. So therefore, A goes like t to the 2/3 power. So the A dot is 10 to t to the minus 1/3, which is about 1 over square root of A. So A is increasing, so A dot must be decreasing. So the A dot must be ever decreasing. So in this, the Freeman equation written this way, so therefore the ratio of two, one more, say one at the radiation matter equality time and compare now, must be, because it's proportional to 1 over A dot squared. So this is A dot at time now squared divided by A dot at radiation time. And since this is proportional to 1 over square root of A, so in terms of A, this is A at the equality time versus A now. Of course, A now is 1 by definition. So this is order of 1 part 10,000. So the universe at radiation matter equality time must have been very flat. So this deviates from only 1 part in 10,000. Now, the successful prediction of light nuclear element abundance at primordial nucleosynthesis time provides direct evidence of the validity of this cosmology back to the 100 seconds after, order 100 seconds after the Big Bang. And so radiation was radiation dominated from the radiation nucleosynthesis time to the equality time. We can show, just a simple exercise, the density ratio at the primordial nucleosynthesis time must have been equal to unity to an accuracy of 1 part in 10 to the 14th. I mean, it's incredibly, had to be incredibly close to 1. Okay. So if it's not 1 itself, it must be extremely close to 1. So the fact that this cosmology requires such an extraordinary fine-tuned initial conditions constitutes the flatness problem. So it must be explained why it has to be so flat, even though gravitational attraction naturally will enhance the curvature part. There is also, besides the flatness problem, also the horizon problem. Our universe is observed to be very homogeneous isotropic at large scale, in agreement with our working hypothesis cosmological principle. In fact, the observed universe appears to be too homogeneous and isotropic. What do I mean by that? You consider two parts of the universe that appear to be outside each other, the horizon. They are so far apart that no light signal sent from one part at the beginning of the universe would have reached another part. But they are observed to have similar properties, suggesting they were in thermal contact in some time in the past. But their present separation seems to preclude they ever achieve any interaction, or let alone thermal equilibrium. How can it resolve the contradiction? So this is contradictory. Far apart, yet they are similar property, yet they couldn't have any causal contact between them. This horizon problem can be stated more precisely in terms of observed isotropy of the CMB radiation. We measure the same black body temperature in all directions up to 1 part in 10,000, 100,000, after subtracting out dipole anisotropy due to our peculiar motion. This observed isotropy indicates at the cosmic photon decoupling age, which is about 10 to the 5th years after the Big Bang, regions then separate by much further than the naive 10 to the 5th light years was strongly correlated. That's a puzzle. Why could it be? How could such a distant region communicate with each other to arrive at the same thermal properties, the same temperature? So this is the horizon problem of the FLRW cosmology. So we have the flatness and horizon problems. In short, cosmic physics suggests that the universe should be highly curved and heterogeneous, yet we observe a homogeneous and very nearly flat universe. This can be modeled by, say, that this FLRW cosmology have a particular set of initial conditions. But these initial values are so fine-tuned, one might wish for a more natural explanation why they should be. Not just say, well, we just happen to be this way. As we shall detail below, the inflationary cost theory of the Big Bang can provide such a natural justification. Okay, that's the end of this first part.